In this video, we are going to continue to discuss the last part of section or topic 2.4. Before this, we have discussed the definitions of a horizontal asymptote as well as the limit of n functions when the x is tending toward positive or negative infinity. So here we are going to continue with the definitions of an oblique asymptote. This is a generalization of the horizontal asymptote that has been discussed in the previous video. Now, what is an horizontal? What is the oblique asymptote? So oblique asymptote happens when you have a rational function where the ratio of the rational function is such that the order of the numerator function is 1 times larger than the order in the denominator function. For example, here the function in the denominator is a polynomial of order 2, whereas downstairs is a polynomial of order 1. Okay, so in this case an oblique asymptote will be developed when x tends toward plus minus infinity. So that demonstrates the idea of oblique asymptote. Let us try to look at example 12. So example 12 is a rational function which is made up of p2x and an polynomial of an order which is 1 times lower than the polynomial upstairs. So here we have 2x squared plus 3, and downstairs, so this is minus 3, and upstairs and downstairs is a function of 7x plus 4. 7x plus 4. So we want to ask the questions, what is the limit of the function when x tends towards plus minus infinity? To be concrete, we just estimate first the limit of the function when x tends to positive infinity. But the same argument would also be applied when you make x to tends towards negative infinity. So the first thing you want to do is to cast the rational function into the form of an residual function and an linear function. Now what I meant by that is this. So you have to perform the long divisions of this function. When you perform a long divisions, then this function will be divided by this function, and what you end up would be a linear function plus an residual function. So the linear function would be in the form of ax plus b, and then the residual function will be something like 1 over another linear function. So let's see how we do this. So you have to then first know what you mean by a long division. So I'm going to perform a long division here. Long division. A long division is an operation of dividing the numerator function by the denominator function. So here you would want to divide 2x squared minus 3 by 7x plus 4. So what you do is first you want to get rid of the factor of 2x squared. So what you do here is that you multiply 7x plus 4 with something to obtain to get rid of 2x squared. So you have to think of a number such that when you multiply this number with 7x plus 4, it gives you a factor of 2x squared. So what you do is you multiply this by an x, right? So when you multiply by an x, this multiplied with 7x will give you 7x squared. But what you want is not 7x squared, but 2x squared. So how do you get a 2x squared? You just multiply 7x plus 4 by x times 2 over 7. Right? The factor of 2 over 7, we'll get rid of the factor 7 and replace it by 2. So you multiply this with this term, then what you get is x squared times 2. But don't forget, when you multiply this with 7x, you also have to multiply this with the plus 4. So you have to take care of this term plus 4 with this term 2x over 7. So what you get is you get a factor of 8 over 7x with a plus sign. This is the result of 2 over 7x times 4. Okay, so that will give you this one. So then you take the difference between this line, 2x squared minus 3 minus this. So you minus this equation from this equation, then 2x squared and 2x squared will be cancelled off. So now you are left with minus 3 minus 8x over 7. So now we have to get rid of x term. In the first instance, we want to get rid of 2x squared, but at this level, we want to get rid of 8x. Now, how do you get rid of 8x? So here, you must add with some other number. What number should you add in? This number has to be added in such that when this number multiplied with this number, it will give you a factor of minus 8x times 7. So what are the number that you have to put? So let's see. So you have an x. So you have the x, then you want to have a number of 8 over 7. And here you have a 7. So what you do is that you multiply this with, I think, 8. 8 times 7. So you have to divide this by 49. Okay. So you multiply this factor 7x plus 4 with 4 over 49, then you expect to get a number of, sorry, I think there is something not right here. I should not multiply this with 49. I have to multiply with another number. So I need to multiply it with at least and 8 and divide it by 7. I think that is more accurate. So let me rewrite this again. So that should be 8 over 7. And I have to use a minus sign instead of a plus sign. So that minus 8 over 7 when multiplied with this factor, or when you multiply with 7x, I'll get a factor of minus 8x over 7. So that would do the job that I want it to. So let me write it down. Minus 8 over 7 multiply with 7x. So what you get is minus 8x. Okay, so that is not right because I need it not minus 8x but minus 8x over 7. So it seems like I have to multiply this by a factor which is not minus 8 over 7 but minus 49 instead. Okay, I think that is a correct number. So you multiply this with minus 8 over 49 with this, then I should get 8 over 7. Okay, hopefully that, I think that should be the correct number. So this number of minus 8x over 7 is obtained from minus 8 over 49 with 7x. Okay, so then this number will have to multiply with 4. So that would result in a number of 8 over 49 times 4. So that will give me minus 32 over 49. Looks like a very complicated number, but anyway, I'll write this in, and then this is a number of 32 minus 32 over 49. Okay, so then what you see is that you have minus 3 minus 8x over 7 minus with minus 8x over 7 minus 32 over 49. So I get this line of equation minus this line of equation. The immediate thing I want to see is the cancellation of the factor of 8x over 7. Then what is left is minus 3 minus 32 over 49. So what is left is 3 minus 3 plus 32 over 49. So this looks like a very complicated long division. I'm not sure my long division has been performed correctly, but if my expressions of performing the long division is correct, then what I would get is an function of 7x over, so it should be 2x over 7 minus 8 over 49. So this is the 2x 2 over 7x minus 8 over 49. And this is what I call the linear function. And the rest is what I call the residual function. The residual function is nothing but just this function in the denominator plus whatever that is left at the end. Okay, so this would appear as the values of 32 over 49 minus 3. Okay, so this is what we call the residual function. Okay, so what I have shown you here is that the original division of an quadratic function by a linear function is now reduced into a linear function in the form of ax plus b plus a residual functions, which is a constant divided by a linear function. Okay, so let's see if what I have done here is correct. So the answer turns out to be 7 over 2x minus 8 over 49, which is correct. And then here is a number of minus 115 over 49. So I suppose minus 115 over 49 is just this number. Okay, let me check if this is true. So I have 32 over 49 minus 3, and this should be equal to 32 minus 3 times 49 divided by 49. So I'm not sure what it is, but you can work it out for yourself. It would be a number which is 49 in the above, in the below, and this is 32 minus 49. I have just finished pressing my calculator and work out that this indeed is minus 115. Therefore, this is a number of minus 115. Okay. Minus 115. So this is how the long division was performed. The rational function is now cast into a linear function and a residual function. Now the important thing to note is that the linear functions is a function which is easy to understand. It represents a line which is represented by a linear function with a slope of 2 over 7, and it cuts through the y-axis at this point. Okay, and then you have this residual function. The residual function that I meant here is a constant divided by 49 and 7x plus 4. Okay, so here then this is a number which I think there's a factor of 49 downstairs, which I have forgotten. Okay, so anyway, the numbers of 115 over 49 is just a number, but what is important is that you always get a residual function which is the form of a constant divided by the expressions of the denominator function in the rational function. So this is what I call a residue function. Residue is just a name that is just to represent whatever left behind after the long division. And what you can show here is that the long division of the ratio of two function, say p2x over p1x, finally would end up to be in the form of a linear function ax plus b, which is in this case this function plus another residue function, which is in the form of a constant divided by the denominator that appears in the denominator function. Here are represented by, say, dx plus e. Okay, so this is the factor that appears or derived after you have performed the long division. So it could be easily checked that the numerator, the denominator in the residual function is just 7x plus 4. But this is generally true, right? You perform the long division of two functions where the denominator function is one order less than the numerator function, you always end up to be like this. Then the limit of taking x to infinity for the rational function is the same as the limit for the linear function added to the residue function, and that is expressed then into the form of ax over b, x to infinity plus the limit of x to infinity c over dx plus d. Okay, so in our previous case here, then the denominator, so the function is like this. So the limit of 2x squared minus 3 divided by 7x plus 4 when x goes to infinity is the limit of this minus the limit of this. Okay, so this is a linear function, this is a residual function, and you would observe that for the residual function, x is always happening in the downstairs. So you can pull out the factor of x and then do some simple algebraic steps to prove that this residual function term, since x is lying in the denominator and there's a constant only in the numerator, therefore this numerator, this residual function, the limit of it is always going to 0 when x goes to infinity. So you end up the limit of the functions p2 over p1 is then just simply equals to the limit of ax plus b when x goes to infinity. And you ask, is this limit convergent or not? That means, does this limit exist or not? The limit of a linear function. So here in our particular example, the limit of the linear function is this, right? So you ask, is the limit of 2x over 7 minus 8 over 49 when x tends towards positive infinity, is this limit exist or not? The answer is no. The limit of this function does not exist, because as long as x keep on growing, then x will go to infinity. So this is a function that has no limit. However, this is what we call the oblique asymptote. It is the asymptote that the function of f behave when x become extremely large. So let me express what I meant by that. So we have a situation like this. Then when x tends towards infinity, then I've shown that this is always reduced to the limit of some ax plus b. Right? So this is shown in the previous steps, and this, when you represent it onto the xy plane, it represents a line of y equals to ax plus b, and ax plus b, and this is the so-called oblique asymptote. That is a straight line where the function f tends to when x is going to infinity. So if you represent this by the graph of the function, we will have the function f to behave either like this or like this, right? So the functions of f will keep on approaching the oblique asymptote when x will become very large. Now it is also possible to work out the oblique asymptote when x tends towards minus infinity. So that will also become the same. It will still give you the same values of ax plus b. So the oblique asymptote will always be the same for the function, whether x is going to the positive or going to the negative directions. If you represent this into these slides, you will see this is the oblique asymptote that the function will tend towards to when x is going to minus infinity. Whereas when x goes to positive infinity, the functions tends towards the oblique asymptote in this manner. Okay, so oblique asymptote is an line which is a generalization of an horizontal asymptote. A horizontal asymptote is basically an asymptote where the slope is taking the values of 0 and the values of c equals to the values of the horizontal asymptote, where a here refers to ax plus b. That is the formula that represents the oblique asymptote. Okay, so that is what we meant by oblique asymptote. It is a generalization of the horizontal asymptote that has a non-zero slope and cuts through the values of the x-axis at the point of b. And for any rational function in the form where the numerator function is one order larger than the denominator function downstairs, will always end up a linear function and a residual function. And this linear function is just the oblique asymptote for the rational function. Okay, so that's all for example 12.